Welcome to SNC's Power Up webinar discussing improved fault detection sensitivity. My name is Brianna Savella, and I'm going to be your host for today's webinar. I want to start off by saying thank you to everyone who has joined us today. We have a wide range of attendees spanning across many facets of the power industry. To make this webinar a great use of your time, we want to make sure we're able to get your input on today's topic. We will be doing this throughout the webinar through a few polls and having a Q&A session at the end. We're going to go ahead and get started. I'm going to launch the first poll, and I encourage everybody to participate. All right, you should see it now. As you all are responding to the polling questions, I do have a few administrative tasks to cover. First, this webinar is being recorded, and the recording will be shared after the event, along with a white paper on mitigating recurring faults with TCC curve shifting. Attendees will also be sent a brief one-question survey. We would greatly appreciate a few seconds of your time to provide feedback on today's content. Attendee microphones are muted, and we've turned off the chat feature. Please use the Q&A function at the bottom of the screen. As I mentioned, we will be doing Q&A at the end of the webinar. And finally, if you do have any technical difficulties, you can also use that Q&A function, and a member of the SNC team will reach out to provide some help. Now that we have those out of the way, I'm very excited to introduce our panelists for today who are going to be sharing their expertise with us. First up, we have Mike Meisinger, who holds an astounding 48 years of experience in the power industry, with world-renowned expertise in protective relaying design, testing, and application. Before joining SNC, he spent 23 years with utilities like Florida Power and Light, and spans protection requirements from nuclear power plants to distribution systems. He has supported SNC's vision of a reliable energy future throughout multiple roles around the world, and he is currently the System Protection Architecture Director at SNC. Next up, we have Kleber Ficini, who's applying his 15 years of power electronics and engineering experience to improve power reliability and resilience on distribution feeders as SNC's Senior Manager of Feeder Automation. In this role, he is responsible for SNC's portfolio of overhead automation products. Finally, I'm very pleased to introduce you to Chet Blackstock, who's joining us today from Sawney EMC. Sawney is a distribution electric cooperative serving more than 190,000 meters in northern Atlanta, Georgia. Chet serves Sawney EMC as the Vice President of Operations, where he applies his nearly 25 years of utility experience to enhance the quality of life of their member owners by identifying and serving their energy needs. Thank you to all of our panelists for sharing your time with us today. I'm going to go ahead and share the poll results and turn it over to Kleber to discuss.
All right, folks, good morning. So we're looking here at the poll results. And so it looks like that it's the main challenges, right? I mean, that folks have is coordination with main feeder devices. Followed by voltage sags due to the testing for fault presence and reclosing. And also they have issues with evolving faults. And so that this seems to be a recurring theme, that we see, especially in the coordination of main feeder devices as they try, as folks, try to increase and to improve reliability of utilities. So I'll go ahead, this is a very good segue of the webinar. And so go ahead and get started here. So today we'll be talking about intermittent and recurring faults and how these can be dealt with. We explain what these faults are, the issues they introduce, and potential solutions, including real-world examples. To start with, let's look at challenges of when the situation is dealt with available products in the market. Utilities are taking several steps for improvement in reliability. The steps vary from increasing situation awareness to segmentation. Segmentation of feeders seems to be a common strategy deployed by utilities. It consists of reducing the number of customers per feeder segment so that fewer customers are affected by faults and outages when this happens. This is accomplished by installing switching devices along the feeders. 2 devices or more devices per feeder seem to be the common strategy for segmentation. These devices can be load break switches, reclosers, or other smart devices. When fault interrupters are used to accomplish segmentation, there is a desire to achieve coordination among them. Therefore, an effort to coordinate multiple time current characteristic curves, also known as TCC, is required. However, when using reclosers for segmentation, often users are faced with few challenges. As these devices lack high end-to-end current sensing accuracy, only 2 or 3 conventional series reclosers can be properly time current coordinated with the substation circuit breaker, and if more are used, miscoordination over tripping typically occurs, and that's what we saw in pole 1. Conventional reclosers use 100% of their available fault energy to test for continued fault presence, which repeatedly stresses the power system upstream of the fault. Reclosing reintroduces harmful voltage sags for customers on healthy feeder segments upstream of the faulted feeder segment, which can adversely affect electronic equipment and distributed energy resources, especially as more DERs are introduced and installed in the feeders in our system. And repeated reclosing can also cause conductors lap, multiplying the problem by creating more faults upstream of the recloser that tripped to clear the initial fault. All of these byproducts of conventional reclosing can cause catastrophic damage to equipment and conductors, as well as decreasing reliability. I'll show you visually what I mean by testing for fault presence using 100% available fault energy. That stress and the stress is caused by it. Here's a video of a test performed in our lab in Chicago, showing how conventional reclosers test for fault presence. You see a face-to-face fault situation, and that's what you're going to see. There is created a face-to-face fault, and that's what you see, a wire across the conductors there. And the device that's testing for the fault is set for 2 fast operations followed by 2 slow operations. And that's why there is increased time and interval between the reclosing activities. So as I show the video, please be advised that the video sound showing the reclosing activity will be very loud. So please be prepared for it. So if you're using a headset, I'd suggest that you move the headsets away from your ears. So here we go. All right, so this is actually kind of what happens in real life, in real world, whenever there are reclosing activities. So it's very loud, very stressful to the system. Another issue all fault interrupting devices must contend with are faults that take time to redevelop when reclosing is practiced, usually due to recarbonization. Some faults redevelop or recur because their conductive fault path takes time to redevelop after being re-energized. And this is what is called recarbonization. This typically happens after fault interrupters using conventional protection practices de-energize the fault path by tripping. They then reclose, re-energizing the fault path, which takes time to become conductive, and subsequently the fault reinitiates. Once the fault reinitiates and is detected, retripping of the fault interrupters occurs despite proper protection in fault interrupter operation. This happens because the conductive path of certain persistent faults is initially high resistive and cannot be immediately detected upon reclosing. However, over time, the reapplication of rated system voltage across the fault path causes it to become less resistive. Once the fault path becomes sufficiently conductive, the fault is detectable and tripping is reinitiated. This can take tens of cycles or seconds, and if it takes a minute, repetitive fault testing sequences can occur. Let me explain how it works. So we'll run through an example here. I'm showing a typical feeder here with two reclosers downstream of the substation circuit breaker. All of the devices here, for the sake of the example, are time current coordinated, meaning that the circuit breaker is set to a lower curve than R1 recloser, and the R1 recloser here is set to a lower curve than R2. This is configured in an attempt to only have the immediate upstream device of the fault to trip. So let's see how it works. A fault happens downstream of R2. R2 trips, clearing the fault, and fault becomes highly resistive before R2 starts to test for faults and can no longer be detected. R2 recloses to test for fault presence by re-energizing the downstream feeder. Detecting no fault, R2 remains closed. Fault path eventually recarbonizes, like I explained before, producing detectable fault current. R2 recloser trips again, reinitiating reclosing sequence until the recloser locks out. And this can happen 3-4 times depending on the set reclosing sequence. Every time the fault redevelops and a reclosing activity happens, with fault still present, full fault current levels and voltage segs are introduced in the system. As a last example, one more example here with using conventional reclosing, let's look at a possible situation when the midline reclosers are not coordinated. The circuit breaker is set to a lower curve than R1, and R1 and R2 are set with the same TCC curve, potentially due to coordination limitations on those devices. And in this situation, there is a great chance that faults happening downstream of R2 will trip both R1 and R2. So let's look at quickly through this example. Fault happens, R1 and R2 will trip to clear the fault. And why is that? As explained, both devices are configured with the same TCC curve, so they will both trip. R1 will start the reclosing sequence. No fault is detected and remains closed. Detecting presence of voltage, R2 will start its reclosing sequence. And detecting no fault, R2 will remain closed as well. After some given time, fault recurs, as system voltage is present in the circuit and the fault path is recarbonized. R1 and R2 will trip, and as R1 and R2 trip, they will go through their reclosing sequence again to test for fault presence and close once the fault is no longer detectable. As the fault path recarbonizes and therefore becomes detectable again, the reclosers will trip again and start their reclosing sequence. This may eventually lead to the upstream recloser lockout, creating unnecessary outages to more customers in the feeder. In this scenario, besides voltage sags introduced in the system by repetitive reclosing, reliability has also been affected, as now all customers downstream of R1 recloser will see a prolonged outage. Okay, so now that we introduced recurring faults, we would like to hear one more poll that we're going to have, that would like to kind of to have the poll for you. And so the poll that you're gonna see there, the question is how to attempt to solve recurring faults and or conductors lap in your system. So the alternatives are don't have a solution, set reclosers to one shot to lock out and don't reclose, vegetation management, increase the delay between reclosing attempts, and I don't experience those. So while folks are going and answering the poll, I would like to remind everyone to please post your questions in the Q&A section. After the presentation that I'll go through here, after that we present the presentation here, we'll discuss your Q&A, your questions within the group. Okay. So let's have a look at the results. All right. So it looks like that camera results in terms of how to attempt, looks like the 41% that is vegetation management, followed by increase the delay between reclosing attempts. One thing, I think the vegetation management is something that works well. However, it can increase the O&M, the operation and maintenance costs as well that utilities have. So it is a plausible solution, but even this is something that it will increase the O&M cost of the feeders as well. Of the budget. Okay. So with that, I'll turn it over to Mike Meisinger. Mike.
Thank you, Kleber. Next slide, please. So Kleber showed you the consequences of using conventional reclosing, where we're applying 100% of the available fault energy to determine whether that fault is still present. Again, this is a phase-to-phase fault. You can see the conductor laying in between the two phases. And what I would like you to take a look at, there are some jumpers leading up to the conductors, and I'd like you to watch them as Kleber runs that video again. Go ahead and run that video, please, Kleber. See those conductors swaying in the back there? With sufficiently slack conductors, that is essentially what happens as the energy goes through the two phases. The conductors move apart, and if they're slack enough, they relax and they move close, could even touch or overcome the air insulation and create another fault upstream. In contrast, we're going to show you now what low energy fault testing looks like, and we're going to essentially respond quickly to this fault and then apply low energy tests. You're going to see two spits, because once we identify a potential fault, we retest again using an opposite voltage polarity. So go ahead and run that video, please, Kleber. Test 1, 2 spits. Test 2 spits. Test 3 coming up. Dramatically different approaches to determining whether that fault is still present or not. And you don't see any significant conductor movement except that from the initial fault. Next slide, please, Kleber. How do we do this? Well, I always describe it as two parts of technology magic. The first is one part of it is the electronics, and the other part of it is the mechanical. So we have to know exactly where we want to initiate a close open operation on the voltage point on wave and be consistent in that choice. Then we initiate this rapid close open operation. So the contacts are closed and open in 1 millisecond. And to accomplish all this, we need very precise current and voltage measurements, including the sensing. And most importantly, none of this makes any sense unless we are going to calibrate the system and run the system during production. So every product is tested with this level of precision and extensiveness. Next slide, please. Obviously, as you can see from the videos, we've avoided significant stress using low energy fault testing versus conventional reclosing. What you may not recognize, though, is that when we're using the low energy testing, the testing is virtually imperceptible to all the customers upstream of that fault interrupter, as is low energy testing. Consequently, because we're using less energy, we reduce the probability of conductor slap. You didn't see those jumpers that were moving so violently during the reclosing sequence moving at all while we were doing the low energy testing. And that's because we're using only roughly 5% of the available fault energy at that point on the system. And we've recently introduced a lower fault finding threshold for weak systems or feeders that are very long in length. And we can now detect faults down to approximately 100 amps. Next slide, please. So there's two benefits, but before we get into the benefits of the recurring faults or the highly resistive faults, I wanted to introduce a concept we call low energy fault finding. And as in Clever's one line before, we have the circuit breaker CB, IR1, IR2, and IR3. And the next click, please, Clever. So as before, TCC3 at the circuit breaker is slower than TCC2 for IR1, but IR2 and IR3 have intentionally been set to the same time current characteristic. Next click, please. So when a fault occurs, we have intentionally expected that both IR2 and IR3 will respond to the fault because they're set identically. Next click. So IR2 now initiates its low energy fault testing, and because IR3 is open, it detects no fault. Click and closes. IR3 now has system voltage and it initiates its low energy testing. Click. But when it is initiating this low energy testing, because the energy level is so low, it is not detected by IR2. Next click. And so IR3 only opens, IR2 remains closed. Next click. This process is repeated as you would in normal reclosing sequences until next click, you eventually reach lockout. But because of low energy testing, we're not reinitiating this tripping of both IR2 and IR3 that was caused by the initial fault. So this enables us to increase the segmentation of the feeder where we can no longer achieve conventional time current coordination. Next slide, please. But does this always work? Well, the intention of low energy fault testing is to differentiate load conditions from fault conditions. But when we have these tree limbs and other highly resistive elements creating faults on a power system, we're not intending to detect those because the energy there, the initial fault energy, is just not sufficient for us to detect. So what we are going to introduce now is the concept of shifting the current time current characteristics and us to detect those, ensuring that the device closest to the fault detects the event and only it locks out, ensuring that the that caused the fault is completely isolated. Next slide, please, Clever. So here again, we have the same one line as we did before, and the fault, which is a fault that reinitiates has initially caused both IR2 and IR3 to trip. Again, IR2 and IR3 are set to the same TCCs. We've done this intentionally to improve the segmentation of the feeder. Okay, next slide, please, Clever. So now, instead of just pulsing or just low energy testing and closing, what we're going to do is we're going to low energy test. But when we close, we are now going to use a faster TCC. So TCC 0 is faster than TCC 1. Next slide. So we tested for the fault presence. IR3 was open, so we did not detect the fault. Because we don't know whether there might be a tree limb in between IR2 and IR3, we're going to remain closed for a period of time, selectable period of time, maybe 2 seconds, 3 seconds, operating on the fastest TCC we have, TCC 0. Next slide. After that period, we're going to shift back to our TCC that we started, TCC 1. Next slide. At this point now, IR3 has been waiting, and we put a hold timer on it to keep it from responding until IR2 shifted back to its TCC1, its normal TCC. Next slide. Now IR3 does the same thing that IR2 did. It applies a low energy test. It's not going to detect that tree limb because that tree limb is going to take time to recarbonize. Next slide. IR3 then is going to close with this fastest TCC. The fault path will redevelop. Next slide. And IR3 and only IR3 will clear the fault. And that's because we've introduced coordination to this sequence of operations. Next slide, please. And eventually IR3 will lock out. Next slide. So what we showed you here is how low energy fault testing and low energy fault finding can be combined with a technique we call TCC shifting to ensure that faults are isolated without the harmful effects of conventional reclosing and the ability to intentionally miscoordinate devices to improve feeder segmentation. Over to you, Chet.
Okay, thanks, Mike. Well, Sony MC is, as Brianna mentioned earlier, we're located just north of Atlanta in Georgia, and much of our service territory is suburban, but even though we're mostly suburban, we still have heavy tree coverage in our area. So trees, of course, contribute or cause most of our outages and present our biggest reliability challenges. So what I'm going to describe to you today is how we utilize the technology that Mike and Clever described in order to overcome those challenges. Next slide. So before we started deploying Interrupter several years ago, our system was comprised of feeders. We only had a few feeders with downline three-phase reclosers. We had many, or still have, many single-phase hydraulic reclosers and some large fuses. And we were only able to squeeze one three-phase device between our circuit breaker and all of our downline devices and still maintain coordination. So when we decided to implement more three-phase devices, we wanted to install more devices in series on a single feeder and still maintain that segmentation. So we had to do this with limited communication as well, because we didn't have the communication technology at that time in order to do any kind of high-speed communication, enhanced coordination. So the things that appealed to us for the Interrupter were two technologies. First was the low energy line testing that you saw in the video with Mike, and also pulse finding that Mike just described that would allow us to put multiple devices in series with the same TCC curves. Next slide. So since then, we've deployed over 500 Interrupters, but as we deployed more and more, two problems started to occur. The first was these reoccurring faults. Since most of our outages are caused by trees, even though we have aggressive right-of-way trimming program. I noticed in the poll that that was the solution that seems to be most frequently deployed, is to have aggressive right-of-way trimming, and we do that. But we still get a lot of green trees falling from outside the right-of-way and limbs breaking off during storms and falling on our lines. And those green limbs frequently cause recurring faults. We also started to notice more and more conductor slack. Now, before we had deployed a large number of devices, we didn't notice it. You really don't start to see that until you get more devices out there. And also we found that some of our pole assemblies made that problem worse, where we had a common pole assembly that we used where our center phase on a horizontal assembly would be installed on the cross arm. And then when you had two of those poles in a row, then your span, the conductors would be parallel all the way through the span. So you had no vertical separation, even though you had adequate horizontal separation. So as the fault passed through those two conductors, that swinging motion would cause them to slap mid-span. So sometimes that would cause additional blinking upline, but sometimes it would drive the upline device all the way to lockout. Next slide. So this is how we deployed pulse finding initially. This is exactly how Mike described. Two interrupters would be in series with the same TCCs. Both would clear the fault simultaneously. The next step, TCC2 or interrupter 1 would test and hold down to the downline interrupter. And that downstream interrupter would then test, detect the fault all the way to lockout, and then remain locked out. So you would get one blink on the interrupter upline, but after that, the interrupter upline wouldn't operate unless you had a recurring fault. Next slide. So this is an example from the oscillography from our system in one of these events. So the top oscillography chart represents two phases, poles 1 and 2, and it's the voltage on those two phases. So you can see the small bump in voltage where the pulse occurs. That's the low energy pulse that Mike described. It did not detect a fault, so you see the voltage increasing and going up to system voltage for some time before it goes away again when the interrupter trips again. That same event is represented by the current below, and on the current chart, you can see where you had zero current. When the contacts closed, because of the scale on this, you can't tell the difference between load current and zero current, but the current stays zero or at load current for 25 cycles after the voltage is applied. So that means that that limb was laying on the line or between these two phases for 25 cycles energized before the fault finally erupted and causing the interrupter to trip back. That's fine if you're doing traditional reclosing, but if you're using pulse finding, that would cause your upstream devices to trip again, and it may cause them to go all the way to lockout. So in these situations, you have increased voltage sags, you have upline devices tripping sometimes all the way to lockout when these recurring faults occur. Next slide. So when we looked at these recurring faults, we looked at data from dozens of these faults, and we found some things that in common between those faults. One was they usually recurred sometime between a few seconds after the line was energized, or a few cycles, up to a few seconds. And what we saw was a majority of those recurred within 2 seconds of the line being energized. The next was that it wasn't that the pulse was malfunctioning, it was just that no fault existed when it first pulsed. And finally, we saw that almost 40% of the faults on our system reoccurred at least once during a test sequence. So every time that it occurred during a test sequence would cause an upstream device to operate. Like I said, if it detects the fault at least once, then you just get nuisance tripping upline. But if it never detects that fault because it recurs time after time after time when you test, then it drives that upline device all the way to lockout. Next slide. So the other problem that we saw was conductor slap. So to illustrate that, in this situation, we've got a fault that occurs downline of interrupter 1, and interrupter 1 clears that fault, but after it clears it, usually 1 to 2 seconds later, a secondary fault occurs between that device and the substation, where the phases come together, they touch and cause a secondary fault, causing your upline feeder breaker to operate. Now, if that fault beyond the interrupter isn't a recurring fault, then the interrupter test, pulse closes, it detects the fault, goes all the way to lockout without allowing the energy upline of it to cause those phases to slap again. But if it's a recurring fault, then it puts the full force of that energy back through the system again, causing the phases to slap again and again, sometimes all the way to lockout. So in those situations, again, best case, you get additional blinking, additional voltage sags that were unnecessary upline. Worst case is it goes all the way to lockout and your entire feeder is out when it didn't have to be. Slide. So when we looked more closely at this conductor slap phenomenon, we initially blamed it on poor coordination. Before we had the oscillography data from the interrupter and all the event log data that we got, we thought we just had poor coordination. Even though our TCCs looked good and they appeared to coordinate, we couldn't detect that secondary fault upline. So we thought that they just didn't coordinate, or that downline device was just not operating fast enough because of a mechanical issue. Conductor slap always requires at least 2 phases to be involved. So it's phase to phase or 3-phase faults. We found, and we found some research that supported this, that it's more frequent for current over 4,000 amps, which is not uncommon at all on our system. We have frequently have fault currents of that magnitude on our system. Also, there's a time component to conductor slap. So the faster you get that current off of the system, the less time that magnetizing force is in play, causing the conductors to swing. So the slower TCC curves made the conductor slap worse. And then I mentioned our pole configurations where we don't have adequate vertical separation. It makes it worse. And sometimes you just have some bad spans. So spans with slack, too much slack, or exceedingly long spans are more subject to conductor slap. Next slide. So when we started to solve these 2 problems, to overcome these 2 challenges, the first thing that we did is we realized what the high precision sensing for the interrupter really means. And one of the things that it allows you to do is to squeeze those TCCs more close together. So it allowed us to coordinate 3 devices in series where we used to could only coordinate 1. So if we have 3 interrupters in series on our system, we coordinate those using traditional methods. But anything beyond that, if we have 4 or more interrupters in series, they still depend on pulse finding to isolate that last segment. So therefore, we had to start using the TCC shifting. So as Mike described, that's where the interrupter shifts to a very fast curve or an instantaneous trip after the pulse detects an unfaulted line. So the pulse comes back unfaulted. It shifts to this instantaneous curve. And our setting is for 2 seconds because, as I mentioned earlier, most of our faults recurred within 2 seconds. So during that 2 seconds, it would be on an instantaneous trip. So if that fault re-erupts during that time, it trips instantaneously and maintains coordination. So this helped to enhance our fault isolation toward the end of our system or toward the end of our feeders. And it reduced conductor slap after testing because you allowed less energy on the system. Next slide. So this is what our protection scheme looks like now. As I mentioned, we can coordinate 3 interrupters in series. If we have a fourth, if it's a really long feeder and we install a fourth interrupter, it doesn't coordinate with the third interrupter, but relies on pulse finding. And we don't have many feeders where they're long enough to justify 4 interrupters, but we frequently get this configuration when we're backfeeding feeders. So we've got one feeder backfed by another all the way back to the station. We may have 6 or 7 interrupters in series where the last several will rely on pulse finding. Next slide. So this is an example of how our system works now using the enhanced fault isolation. So in this example, interrupters 3 and 4 have the same TCCs. So both trip simultaneously initially. Interrupter 3 pulses, doesn't detect the fault, stays closed. And then interrupter 4 pulses all the way to lockout, assuming it detects the fault. If it doesn't detect a fault, then it shifts to the instantaneous curve. If the fault re-erupts within that 2-second hold time, it trips instantaneously, maintains coordination with interrupter 3 all the way to lockout. Next slide. And then if we have situations that lend itself to conductor slap, and I will mention that these situations lend themselves more to voltage sags as well because they involve high magnitude fault current. So in this example, we have a fault beyond interrupter 1. This is a phase-to-phase fault. It causes a span to slap, conductors to slap up line. So interrupter 1 clears the initial fault and the circuit breaker clears the secondary fault. Substation breaker closes. Hopefully by that time, the phases aren't swinging so much that they slap again. Once the interrupter detects system voltage, it tests. If it detects the fault, it tests all the way to lockout successfully and doesn't operate the circuit breaker. If it's a recurring fault, then it initially tests with no fault. If that fault reoccurs within 2 seconds, it trips instantaneously, allows less energy through the system, doesn't have enough fault current or time. It's really the same fault current, but less time, and able to have the phases slap, and it operates all the way to lockout without subsequent feeder breaker operations. Slide. So we've successfully utilized these 2 technologies to solve our 2 sectionalizing problems, both recurring faults and conductor slap. So as I mentioned earlier, we have about 500 interrupters on our system. We deploy them utilizing these two technologies. And they've greatly enhanced our reliability. We, as most utilities, we put a lot of time and money and effort into maintaining reliability. And these have become 2 important tools that we utilize to do that for our customers. So that's all. Back to you, Brianna.
Thank you, Chet. And I do want to thank our other speakers, Kleber and Mike. This has been great. We have a very engaged audience. Thank you for sharing these insights with us. I'm going to go ahead and jump right into the Q&A, what we already have. I will remind the audience, you can continue to use that Q&A function at the bottom of your screen, and we will get to as many questions as we can today. The first question looks like it is for Chet. What was the typical root cause of the 2 to 3 seconds durations for the reoccurring faults, and was the primary cause of the conductor slap wind?
No, okay, so 2 parts to that question. I'll answer the second one first. No, we're not talking about wind-induced conductor slap. So this is fault-induced conductor slap. So this is where the fault current passes between the 2 conductors, and the magnetizing force forces those conductors to swing away. And then when they swing back together, they actually make contact. So I can't answer the question of why it's just 2 to 3 seconds. That was just based on what we saw in our system. We analyzed dozens of faults. And you may recall the picture that Kleber showed of the limb laying across the phases. That's really what we're talking about. So what happens is that limb lays there and it requires voltage for some time before it carbonizes a path across it and allows that fault to reoccur. So on our system, we've just seen it happen within 2 seconds. Sometimes it takes longer and there's nothing you can do, but most of our faults occur within that 2 seconds.
Okay, thank you. The next question, I think, Kleber, you mentioned during your section that voltage sags are becoming more of an issue for some utilities. Can you expand on that?
Sure. Yes, I think, Brianna, I think that the voltage sags, I mean, as even like Chad said, this is used to be that voltage sags were very harmful, I mean, for industrial utility, for industrial customers, because I mean, whenever there is a voltage sag, I mean, like equipment in a facility can disconnect because of the sensitivity, on the sags. And one in chat, and also we can talk more, but I've heard of some folks of some utilities, that actually that serve big metro areas, that residential customers are starting to become very annoyed with that as well. And so why is that? So as you see in our homes, in our houses, right? I mean, we have a cable box, we have internet. I mean, there are more people working from home, and that becomes an annoyance whenever there is that flicker, that voltage sag, and you're trying to watch a movie or trying to watch a football game, you're trying to work on a call. That becomes very annoying. And I think that another reason, that we have seen that, like I mentioned, distributed energy resources are starting to become more prevalent in the system, in the utility. And today, DRs, they are supposed, whenever there is a voltage sag, whenever there is a frequency disturbance, DRs, they trip offline, but as penetration increases, later on in the future, utilities, that becomes more like they rely more as a source of energy. They will want that source of energy, that asset to remain available. So voltage sags will be detrimental to the operation of the DRs. And Chat, what are your thoughts on that?
Well, so we receive a lot of complaints from adjacent feeders during high fault current faults for voltage sags. So, some of the things that help your voltage sags also help your conductor slab, because if you think about it, both are caused by high magnitude fault currents, and both are exasperated by slow TCCs. So the faster you get that fault off the line, the better. So what that allows you to do is that initial trip, you're probably going to get that sag. And then what you're trying to avoid, though, is subsequent testing. If you're doing full energy reclosing, then those voltage sags are going to occur time after time. Where if you can utilize the pulse closing and have low energy, then you don't experience that additional hits on your system and the additional sag. So yeah, we've experienced that for sure.
I think that leads pretty nicely. We have another question related to DERs, and Mike, I think that this came up when you were speaking. Would TCC shifting and pulse finding approaches also be feasible for feeders with high DER injection and eventual reverse power flow?
It's an interesting question. I guess the answer really depends on what the contribution from the DER is in terms of physical current. In a lot of cases, if it's inverter-based DER, you're not getting much more fault current than the load current they can supply. If you're looking to detect a fault event and there's not an appreciable difference, bidirectional fault detection is not a problem. As long as there's a difference between the normal power flow and the reverse power flow, you should be able to accomplish that detection. It's just a friend of mine, Dr. Alex Apostolov from Omicron, one of his favorite answers is, it depends. You need to know a little bit more before I would say conclusively that, yeah, it's not a problem. It is a consequence of the configuration of the DER relative to the feeder and what the normal power flow would be.
Okay, thank you. Chet, I think this next one is for you. You mentioned that you were already doing tree trimming and vegetation management. And so why did you have to implement these solutions in your system?
Well, I think a couple reasons. One is because even though we have aggressive right-of-way maintenance programs, we get a lot of green trees, for instance, that fall from outside the right-of-way. We have a lot of pines. So when you have a green pine, they're often very tall and very thin and will literally lean over onto the pine, especially in heavy wind, lean over onto the line, especially in heavy wind situations and in ice storms and situations like that. So those green limbs that break off during high wind conditions, they often blow all the way into the line, and they set themselves up for recurring faults.
Thank you. Okay, Mike, I think this one's for you as well. How are you able to time current coordinate more series fault interrupting devices? And why is using TCC tolerance bands more effective?
Well, to achieve or to improve your ability to coordinate multiple series devices using time current coordination, the narrower that you can make. Okay, let's talk about tolerance bands to begin with, because I think this is part of the solution. In the past, many utilities have only chosen to represent the time current characteristic as a single line, a nominal single line. And to achieve coordination, they applied what we call a coordinating time interval. When it was electromechanical relays, that was 20 cycles, 330 milliseconds. Okay. But as we began to produce electronic protection devices, we now had a more repeatable performance, and that enabled us to establish tolerances of the device. So you have the measurement tolerance of the current sensor, and an iron core CT is the most common. We, in our products, use Rogowski coils, which are much more precise and linear across the load and fault current range. But an iron core CT typically has a 10% tolerance. So when I do this, I account for a plus or minus 5% measurement error of the current due to the iron core CT. And then I can go to the protective relay manufacturer, and they publish the tolerances for their current measurement. So in addition to the 5%, plus or minus 5% for the current transformer measurement, you will typically see another 3.5%, 4% plus or minus for the current measurement. And then you have the time. Okay, so the timing duration also has a tolerance, and that can be another 4%. So as you stack all these tolerances together, plus the fault interrupting time of the device itself, which is often 2 or 3 cycles, your tolerance, your band of error from the nominal curve now establishes the minimum response and the maximum response of that fault interrupter. And if you do that, you will find that you can achieve better coordination because you're dealing with these tolerances. Coordinating time interval using a single line was trying to roll all of those unknowns in a factor. But if you actually about this a little more scientifically, you'll find that you can achieve better coordination regardless of whose device you're using. But if you now are using more precise sensing with the Rogowski coil, and you're more precise in your measurement of the current, and you're calibrating all of this, okay, that's the other key, calibration of their measurement. So if you're factory calibrating this, all of a sudden, the band of your time current response is much narrower. And because it's much narrower, you can sandwich more devices in series. So that really is how I counsel people, but regardless of whose product you're using, move away from the single line approximation and actually do something a little more scientific and actually replicate the minimum and maximum response of that device, including its sensing and its measurement.
Thank you. All right, I'm going to try to get a couple more questions answered before we need to close out. So the next one I think could really be for any of you. Is there any benefit to using low energy fault testing where utility is trying to improve reliability by tying two feeders together using a normally open fault interrupter?
Chet, you probably do that already.
If I understand the question correctly, so I guess they're referring to which would be typical in our system, where we utilize an interrupter between two feeders as a normal open point. So does that sound like what they're asking? Yeah. So the benefit is this. So originally we asked ourselves if it was worthwhile to place an interrupter at a normal open as opposed to a traditional switch or a recloser. And what we found was in those times during large storms, or if the crew hasn't identified all the faults, that you get the benefit of that pulse when you try to close. So if you've got a conductor down or a hazardous situation out on the line, you get the benefit of that low energy pulse as opposed to slamming that system with a full energy fault. So I would say it leaves you more margin of error when you're re-energizing lines during a storm. Is that, okay, Mike, you think that answers that question?
Yeah, absolutely. A lot of folks use automated loop restoration schemes, and typically, classically, 50, almost 60 years ago, there were just a midpoint recloser on each feeder and a tie point normally open. And what you never knew was when you closed that point, whether you were going to close onto a fault or not. The fault was in the last half of that feeder. You were closing onto a fault, transferring that fault to your healthy feeder. And so to your point, Chet, being able to low energy test before you close to transfer unfaulted load to your healthy feeder saves that healthy feeder from voltage sags due to closing onto a fault.
All right, thank you. So now I have the same question for each of you to close out the Q&A section. What is one key insight or piece of advice you'd like the audience to take away from today's webinar? Putting everybody on the spot. Clever, can we start with you?
Sure. So I think that, the insight to me is the low energy test, right? The benefits that it can bring. It really, as Chet and Mike, just mentioned, that low energy test, it has a lot of applications, right? You have the TCC shifting, you have the post finding that, the ability to perform post finding, ability to, when you run into the limitation of coordination, you can set all of your devices right in the feeder with the same curve, the same TCC curve, and recover from it using the low energy test. So I think that low energy testing, it has revealed itself, it has become an application where like a feature that can be used in several applications. That's, I would say, the main insight, that I would like the audience to take away, that with this, a lot of other solutions, can be unlocked by that, while maintaining high reliability of the system.
Thank you. Mike?
After 48 years of practicing power system protection, my learning curve is vertical. So what I would encourage the audience to do is ask questions, be curious, and ask for help, because it's an industry, it's a practice that over time you develop more experience, and those resources are out there to help you. If you've got a problem, talk about it, ask the question. Don't be embarrassed that you don't know. And it's a wonderful industry to follow. I'm still having fun after 48 years.
Thank you, Mike. And Chet, can you close us out?
Sure. I would just encourage everyone to utilize the data that you have. some of the problems that we talked about today were not evident to us until we just started deploying more and more devices and our system became more complex. And it was through analyzing that data that we found the whole phenomenon of emerging faults and conductor slaps. So utilize the data that you have. It'll point you in the right direction of what problems to go try to solve. And like Mike said, don't hesitate to go seek help to solve those.
Thank you so much to all of our panelists today. This has been a great session. I know we're right at the 12 o'clock mark, so I just want to remind everyone really quickly that we will be sending out a recording of this webinar along with a white paper on mitigating recurring faults with TCC curve shifting. So that will be going to all of today's attendees. As you leave, you will be prompted with a 1-question survey on today's webinar. It would be amazing if you could provide a response to that. And to close it out, I just want to thank all of our attendees for spending your valuable time with SNC. Thank you to our speakers again. Have a great rest of your day.
Bye-bye.